All right, Miss Jody here for the second video for our chemistry class that is just helping us solve the two problems that we had in the last video. Sorry, I meant to make this one the next day, but I got busy with trying to get all the videos done and figuring out how to do all of them. So sorry you've had to wait so long on solving this one, but I'm sure you were able to just look in the book. But just as an explanation here, we had this going along with our topic of bond energies. And so the question was, to make ammonia, nitrogen and hydrogen are reacted at high temperatures to this equation, which is N2 in its gas form with 3 moles of H2 in its gas form, and then 2 NH3 in its gas form. So the question is, what is the change in enthalpy? If you remember, enthalpy is going to be the amount of energy in the system, in this particular, in the bonds and such. And so when it comes to trying to figure out the change here through this chemical reaction, then we're able to calculate that. And how we do it is, and also to figure out whether it's endo and exo, is to draw out this reaction here with the Lewis dot structures. So with the Lewis dot structures, we're able to draw out the first one. This is nitrogen, triple bonded, N2. And then you have 3 sets of H2. Here's H2, 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 in one single bond. And then you have one molecule or 1 mole of nitrogen, NH3, so 1 nitrogen in the middle and the 3 H's, and then another one, N and 3 H's. So once you draw that out, that helps you visualize the bonds, which are where the energy is going to be at. And so we take those bond energies and we can just do some simple calculations to figure out the change in the system as the reaction went on. Okay, so first, if we look at nitrogen, we realize that triple bonded nitrogen is 942 kilojoules per mole in that in those bonds, 1 whole mole of that. And then with the hydrogen, the H2, it's 432 kilojoules per mole in these bonds. But here's the thing, we have 3 of them, 1, 2, 3. So we would have to multiply that number by 3, and that would create it, or that would calculate it to be 1,296 kilojoules per mole. Now, because we have 3 moles of that. Now with this one, we have 2 sets on the product side, and I guess I should do this so we can draw a line between, this is the reactant side, this is the product side. And so with the product side, I have these bonds of NH or HN. So these NH bonds, 1, 2, 3, 4, 5, 6, there's 6 of them. And each NH bond is going to be 386 kilojoules with that energy in there. So what we have to figure out is what's this change in energy. Now, once it goes through this breaking apart and reforming thing, what's going to be going on here? So it's easy to calculate now that we've drew it out and found the bonds to figure out what's going on. So on the product side here, we have 942 kilojoules per mole, and then we have 1,296 kilojoules per mole for this. And if you add those together, so on the product side we had 2,238 kilojoules per mole in the system. And then in its reaction, it goes through, and then in the end it's going to form this. So when it forms this, we've got a different amount, because that's what happens in chemical reactions as the bonds and they rearrange. And so how much energy on this side? Well, we have those 6 bonds that are 386 kilojoules, which made 2,316 kilojoules per mole. And all we have to do is simply subtract it. So in this beginning of it, you had 2,238. In the end, you had 2,316 on this side. And so when you subtract it, you end up getting negative 78 kilojoules. So if you remember from our lesson, once you see a negative sign, that's going to be an indicator that that energy has been released on this side of the product as an exothermic reaction. Okay, so we would look at that and say, oh, negative 78 kilojoules, and so therefore I know that this was an exothermic reaction. Okay, and then our second one is the on the next page, and this one I did a whole page for, so it gives us a little bit of room here, and you should also, unless you write really small and can fit it in on the other pages. So we already wrote this one in our first video. So the complete combustion of methyl alcohol, which is CH3OH, is used to power some experimental automobiles. What is the change in enthalpy of that reaction? Now I should have noted, and I didn't notice this when I was writing it out, but whenever we look at this, we say, okay, why is there H3 over here, but then there's also an H over here? Wouldn't it be CH4O? But scientists, and you probably remember when we were looking at the hydroxide and all that, sometimes scientists will write things in a certain way so that you can understand the Lewis dot structure. So this one might have thrown you off if that wasn't something that came to memory, and hopefully you looked it up in the book if you got a little confused. But that would help you with drawing out your Lewis dot structure. This is to help us understand that the O and H will be together, and then the C and the H3s will be together. So when you draw this out, you see the C in the middle, and you got your 3 H's here, and then that's going to be bonded with the next set, the OH, which will be the O, and then bonded with the H. And so that way you have the right amount of bonds for your counting, okay? And so the thing is, when I drew this out, the one thing that you would have to have made sure you did also was to balance it, okay? And when you first wrote it out, of course, being complete combustion, you would have had to figure out your own formula. So you'd have this guy, which you knew, and then you would say complete combustion. Well, that means it's going to be reacted with oxygen, and it's going to create carbon dioxide and water as its products, because that's complete combustion. So you would write that out, balance it, and so that you have the right amount. Then you would start calculating your bond energy. So it will take a lot of room if you're drawing all these out. Okay, so now in drawing it out, we have 2 sets of this methyl alcohol here. And so we've got this one drawn and this one drawn, keeping the OH here. And then you have your 2 sets of O2. Your set of 2 O's, but there's 3 of them now that you've balanced it. So 1, 2, 3, and then you've got your product side, and I'm going to draw a line here just to keep it, since it gets a little busy on the page here. And on the product side, I kind of have to tilt it a little bit, but you can see that we have the balanced 2 sets of CO2. Here's CO2, CO2, and 4 sets of H2O. 1, 2, 3, 4. Okay, so then now it'll just be all about the calculating. And so if you were doing the calculating, this is my calculations to try to keep them straight. I have 6 sets. If I look at my CH bonds, I've got 1, 2, 3, then 1, 2, 3. So that's 6 of them with the CH. So I got 6 CHs, and then I figure out what each of those will entail, how much they each bond. And 1 CH is 411. So then I would do 411 times multiplied by 6. And then I find my CO bonds. Here's a CO. Okay, so 2 of those, and each one of those bonds are 358 kilojoules per mole. And then I'd look and say I have 2 OHs, so this one to this one, that one to that one, will become 2 multiplied by 459 kilojoules per mole. And then don't forget this one here. I've got these double bonds. So double bonded O's are going to be have the energy of 494 kilojoules per mole. And so then I would obviously have to multiply that by 3. And so when I did my multiplication, I would come up with these numbers. So this is me multiplying that by 6, there, that by 2, there, that by 2, there, and then making a total in the end. And then, of course, this 3 times multiplied by that would be that. And then I'd have my total. So I added them all up, and it would come to 5,582. And then after that, I'd go to the product side, and I'd say, okay, what I got on the product side, I got 4 sets of the C double bonded to O. There's this, so I got C to O, those 2 bonds, C to O, those 2 bonds, C to O, those 2, C to O, those 2. So 1, 2, 3, 4. 4 full bonds of a C bonded double O. That would be 799 kilojoules per mole in each one of those. So I'd have to multiply 799 by 4 because I got 4 of them. And then also I look at my H's and O's, and I got a whole bunch of those because I got H and O there, H and O there, H and O. So I'd count them 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 bonds of O bonded singular bond to H. And then each one of those bonds would be 459 kilojoules per mole. So I'd have to multiply that by 8. So when I multiplied 4 by 799, I got this. Then I multiplied 8 by 459, and I've got this. Then I totaled it. Once I totaled it, it came to 6,868. So I have on this side of the system 558 in my reactant side, and then in my product side I had 6,868. And when I subtract that, it comes to negative 1,286. So my change in enthalpy is negative 1,286 kilojoules. So therefore, being negative, I've got exothermic. Now the book did note that we should always note that combustion reactions are always exothermic, which makes sense because we understand combustion when we think of burning and such. Okay, so that is those two questions. I hope that helped.